Hello, welcome back to our course on data structures and algorithms. Currently, we are in Unit 3, which is all about binary trees. We started this unit by studying binary search trees, and we've studied those pretty intensely, right? So now I want to look at just binary trees. So not binary search tree, but just a regular binary tree. Specifically, I want to talk about completeness. And that's going to lead us into a new application for binary trees. So this will be just kind of theory based. We'll have kind of a fun little exercise to go with it. But this is really about getting the techniques down for what we'll need to make a new kind of data structure with this. So, in some situations, which we'll discuss in the next lesson, what we really require is not that things be in like a certain order, but that we have a completeness in our binary tree. So, implementing a tree using an array makes keeping a tree complete much easier, more easier than using the kind of linked structure that we've been using. So recall that a complete binary tree is one where every level is filled except possibly the bottom level, and that is filled from left to right. So if we were to add another node to this binary tree, we would simply do that right there. Then the next one would come here, etc. So if we use an array to make this binary tree, then what we're going to do is we're going to basically be assigning these nodes an index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. And if we keep a reference to a variable called size or next index, then we will be able to immediately add in basically in O1 time, right? We'll be able to add to our binary tree in O1 time instead of the O login time of a regular search tree. So that being said, let's go through some math involving this. So we're using an array to implement the binary tree. Instead of using a link to left and right, we're going to have to use mathematics. So keep in mind, we're doing just a regular binary tree, but we could totally do a binary search tree with this as well. We would just have to have like an expandable array that's really big. That allows us, to not worry about balance. But that ends up being kind of a waste of memory. So when you're doing a search tree, it usually is better to do linked data structure. But I did want to mention that we could use an array here, even for search trees. So suppose that the root of our binary tree is assigned to index 0. Okay, so this is our root right here. That right there is our root. Then the child that's there is 0, okay? And that's root right there. That's root, right? Then the left child is at index 1 and the right child is at index 2. Now the left child of 1 is index 3 and the right child is 4. And the left child of index 2 is 3 and the right child is 6. So we continue down this pattern, we can start seeing the way things work out. So where would node 5's left child be? Well, node 5's left child would be 11 and 12, right? 11 and 12. And the parent of the fifth one, what's the parent of the fifth one? Well, you can see here that it's 2. So can we see kind of a pattern going on here? When the node's index was 1, we had a child index 3, and the right index was 4. So this is always one more than that. That's clear, right? The right index is simply one more than the left index. Well, how can we figure out what the left index from the node index is? Well, when we had 2, it's a 5. 3, it's 7. 4, it's 9. 5, it's 11. So 6, it's 13. That's right. We're timesing it by 2 and adding 1. And then this is 14. So for the nth child, we know that for the nth node, its left child must be 2 times it plus 1, and its right child must be 2 times it plus 2. And if you ever forget this formula, just draw out this picture here for a complete binary tree and just see the pattern. It's not that hard to figure out, right? What about for the parent? Well, the fourth child had a parent of 2. Third child had a parent of 1. Second child has a parent of 0. You'll notice, though, that some children are going to, 2 children are going to have the same parent. So let's talk about the index for 5. Well, we know that the 5 came from 2, just like 6 did, right? Oh, 4 didn't come from 2. 4 came from 1. Okay, this was not right. Let's fix that. Sorry about that. So 4 came from 1. Yes, the 5th child, node index 5 had a parent of 2. Node index 6, what did it have? It also had a child at index, a parent at 2, right? So can we see a pattern here? What's going on? What about 7? Well, 7 goes to 3, and 8 goes to 3. Well, what is 7 divided by 2? Well, for integer division, it would just be 3, right? But what is 8 divided by 2? Well, that's 4. So, we don't want to say if you're a left child, subtract 1 if you're a right child. Don't. We want to just have a single formula that works. But what if I subtract 1 from 7 first? I do 7 minus 1 and then divide by 2. Well, that's 6 divided by 2 is 3. But if I do 8 minus 1 and divide by 2, I get 7 divided by 2. Well, that's also 3 with integer division. Let's try that with 9. 9 minus 1 is 8, divided by 2 is 4. 10 minus 1 is 9, divided by 2 is also 4. So because of the glories of integer division, right, that causes us so much headache sometimes, but in these rare cases is really helpful, we can get a very good formula. We're going to just do the index minus 1 first, then divide by 2. So I call them algorithms, but they're really mainly formulas. The left child of a node is at index n. It's index 2n plus 1. The right child of a node at index n is at index 2n plus 2. And the parent of the node is at n minus 1 divided by 2. So what would you do if you had to traverse this tree? So let's go through. Let me get a clean copy of that, and let's talk about traversing. So we've seen that we have depth first and breadth first traversals. The only breadth first that we've looked at so far has been level order. It's like a typewriter. And if you recall, we had to use a queue to do that. So this is the node at index 0. This is the node at index 1, 2, 3, 4, 5, 6, 7, 8, and 9. Well, I'm going to have in my array, whatever this data is that's at each one of the nodes are going to be in my array in that order. So when I have my array, it's going to be, whatever this data is. If these are, letters like the letter A, that's going to be an A. If this is the letter R, that's going to be the R. If this is the letter C, that's going to be C. Maybe that's a D. Maybe a Q here, because we're not a search tree, right? Not an order. So if I do level order, I just got to start at index 0 and loop through the size, because we probably are using an expandable array to do this, or if you know how many elements you're going to have originally, or if you want to limit the size. But probably an expandable array, so we can't just use the length of the array. We need to use a size variable. So for me, my size is 10, so I would loop through less than that size. But it would just perfectly be in level order to just start here and print. So it turns out level order is really nice and easy. But what if we were trying to do, like, say, an in-order traversal? Well, it's not going to be too often that we want an in-order traversal, a complete tree, but it's worthwhile to talk about it in case we need to. So if we're doing a recursive traversal, we would use, we would just be sending indices of nodes back and forth. So for example, an in-order traversal, I would write a recursive method, like if I was just printing or adding them to a list, I might say void recursive in order, and I would take actually an index of the array, and I would first time I call it 0. And we're supposed to return if this is a null. Well, let's see here. If index is greater than or equal to whatever my size variable is, that's when I would return. Okay? Else, what we want to do is we want to return, or in this case, simply call if we're just printing, rec.io with the left child, which we know is 2 times the index plus 1. And then we want to print or visit where we're at, and then call rec.io on the right, which is 2 times the index plus 2. So that would be the way we would traverse it recursively. How would we traverse it iteratively? Well, we know that an iterative traversal is most easily done pre-order. You have to make a slight tweak with the in order and post order, but they require a stack. Usually it's a stack of nodes, but this time it's going to be a stack of indices or just integers. So it's going to be a stack of type integer. And what we would do is we would start by feeding this root index onto the stack. And then we would just keep the in order. You just keep looping while the stack is not empty. You pop something off the stack, and then you push on the stack the left and right indexes. But if you recall, because stacks kind of reverse everything, you do the right index, then the left index. All right, then we pop off the stack, and you offer to the stack the right and left index. So in case this will be a 4 and then a 3. Then I pop off the 3, and I offer an 8 and a 7. I pop off the 7, and I offer 15 and 16, which turn out to be nothing. So you would probably want to make sure before you add to the stack that node is actually less than the size. And that's how that would go. Remember, with the in order, you have to kind of use a little different algorithm. You got to first start with either a reference to the a current node, so you have a current index, and then it's while the stack is not empty or current is not null. Well, how do we say current is not null? Well, your null index is going to be an index that's greater than size or less than 0, something like that, maybe. But in this case, it would be something greater than size. So the in order is going to be challenging, but I want you to give that a try. I've got a nice little assignment. I'm just going to kind of share it with you right quick. So maybe you've seen The Princess Bride. If you haven't, well, that's a shame. You should see it. It's wonderful. But famous line, right? In the film. And we're just going to play with it and see what happens. So I want you to create a class called Word Arranger, and Word Arranger is going to have a constructor, which uses a parameter of words that are space separated to create a complete binary tree, right? Not a search tree, right? And I want you to perform the methods pre-order, in-order, post-order, and level order that return a string of the words in the complete tree. So to do that, you probably want to use an iterative method. That way you don't have to make an additional variable to hold your strings. You can just take care of it all right there. So it'll be challenging, but I want to see you try and do that. The pre-order we kind of went over. The in-order and post-order, you have to pull out those algorithms. And level order is super easy. And we're going to call it with this main method here with the words, hello, my name is Inigo Montoya. You killed my father. Prepare to die. And you should get some pretty wacky results. So good luck with that.